easy to make mistake when you go that route. And at the end, the answer is the same, so why do you make life difficult for yourself? Yeah?
Is this already posted on Canvas?
Yes. It's not? I'm sorry. Yeah, Canvas is very confusing. It took me a long time to go through all the options, so you have to just spend at least 15 minutes go through the whole site to find where the lecture is posted, where the video is, where the homework solution is posted, where the post-up reading is, etc., etc. Okay? All right, so those two steps is critical, and now we can start looking into the momentum equation both in x and y direction. We have spent a lot of time in the x direction. I'm not going to go through that. I did mention the y equation prior lecture. Only change is now you have subscript y instead of x on the forces. Velocity instead of u, which is parallel to x, replace that by v. So velocity parallel to y. Other than that, they look very, very similar. But it is two physical equations that are not coupled. So knowing which control volume we choose, which is now this one, and I draw all the pressure around them. This is now, for the first time, not a rectangular or white cylinder control volume. It's almost arbitrary shape. But everywhere is PA. What's the net pressure force both in x and y direction? Zero. Do you get it? Do you understand why I give you that? Half an hour ago, draw you a diagram of an arbitrary shaped control volume versus a circle, and it's for this reason. No matter how I cut it, the net pressure is cancel out in both directions. Let me stop and make sure you understand that. Do you? Okay? The other forces are the anchoring force, and again, if I assume them in a different direction, will the answer change? In other words, if I go back to this diagram that's given the reaction force in the x is upward along the plane and y is normal to the plane as shown pointing upward. If I reverse that order, will the answer change? Well, it will change, but at the end, you get the same numerical answer, right? So as I have chosen it, the forces are positive, and the x direction force is 0. Okay? This is step 3. Divide and conquer one piece at a time. So any question about this one? Then the next step is just to put all those forces in my xy momentum. On my left-hand side, the momentum equation, so what I have left with all the dust settle is what I've shown here for x and y. The fun start when I go to step 5, where now I'm dealing with the right-hand side of the x momentum equation. And that's all I will do. I will let you do the y momentum equation as a homework on your own. It won't be collected. But it's important for you to go through this 4-step on your own and look carefully by some of the footnotes that I have. All right? So, x momentum, m dot u out, how many stations? How many stations? 2. 2 and 3. In is 1. Only here. So I'm going to break it up into m dot u2, parenthesis, positive. M dot u3, positive, because it's out, momentum flux. Minus is the in momentum flux with m dot u. And here is where the rubber hit the road. What is my m dot in all these 3 terms? Is there a sign with it? No. It's only a scalar. So at 2 will be rho v, area h2. No sign. Velocity is already chosen to be perpendicular to the area, so I make it very easy for myself. Second term, change it to H3. By the way, the problem statement stated the velocity is everywhere equal to V, and that you learned in another 2 lectures of 3 is because of Bernoulli. But right now it's given. Then the last term, doing with only the m dot first, is rho V H1. No sign. Okay, yes?
Are we saying that the area is H1 because we're assuming the thickness is the same throughout?
It's a 2D problem. What does that mean? 2D problem? 2-dimensional? So every cut along this is the same. So this is per unit depth, per unit dimension into the paper, right? So it's h times 1. Okay, everyone clear on that? 2-dimensional. So any question on the m dot at station 2, 3, and 1? Now do the velocity for me. At station 2, what is the velocity and the direction? Station 2, right here. V plus or minus? Positive. You get it? Okay, now station 3, coming downward. Same V, plus or minus? Negative. You get the sign right? Then continue on to the velocity at station 1, which is the component parallel to my x. So you have to use trigonometry to resolve the velocity here into the direction along the plate, which happen to be V cosine. Okay? With a plus sign. And that's it, you're done. You're done. Yeah, the rest is bookkeeping. The physics is done. Any question? So you put them all together, resulted in the x momentum equation here, which is one of the 3 equations needed to solve for 3 unknowns, x2, x3, and ry. Then this is your homework. When you're done, you have now 2 equations on the book. Check the sign to make sure all these footnotes, you understand. And now put everything in the momentum equation. I'm using 1 equation to solve for the 3rd unknown. What haven't I used yet? What haven't I put down? Continuity. Continuity. And if you do that using continuity, and you should check also, with the 3rd equation of continuity, the problem is solved. And the answer is in the bottom for H2 and H3, as well as Ry. And you can check symmetry to see if your answer is physical and correct. So I'd like you to look at this in more detail. There are many other pieces that I don't have time to go through, nor should I, because I want you to read that on your own. And what I'd like to spend the remaining 3 minutes on is on the homework. Problem. A circular nozzle with a band. So the band you have to deal with, those previous problems, the band go 180, so it's a 1D problem. Now the band is ending at a 45-degree angle with the free jet coming out at the exit. Horizontal, I hope you know what that means to you. And it's very peculiar. It's what I call somewhat of a reverse problem in that the forces is given. in the problem statement. And you're asked to find the flow rate. Kind of different than what the normal problem you have done in the past, which is you're given all the velocity, or you can find them from continuity, and you're asked to calculate anchoring force. So this is just a little twist. Instead of doing the velocity, I give you the force, and you find the flow rate. Yes?
So the top prototype is horizontal, and then it makes a greater than 90-degree turn?
No. The whole thing is horizontal,
Oh, okay.
and you make a 45-degree turn. The whole elbow is on the table. Right? I will leave it at that. I think if you use the momentum equation in the x direction and continuity, you will get to the answer. And part B, after you're done with that, it asks you for direction force in the y direction. So choose your control volume carefully. Carefully. Anyone want to make a hint as to how you would like to draw the control volume based on what we have done? If you want to help your classmate. No? No one want to help each other? Yeah?
Draw it perpendicular to the output and perpendicular to the inlet.
You will do the same thing we did with the plate, and I'll leave you at that. The next problem is a cone has certain weights which you are asked to find, supported by a stream of jet of air, not water, and it's split asymmetrically. Right? There are other statements given in the problem, but again, this boils down to how you want to choose your control volume, which will make the life a lot easier. It's obviously a use of momentum and continuity. How would you want to choose your control volume? What would be, given the plate problem and this problem that we have visited, what would you